Hi, my name is Quentin Tradup. I'm a fourth year at Augsburg College. Currently studying biology with a chem minor. Today I'm going to be talking about how the immune system responds to bacterial infection within the central nervous system. Alright, to give you guys a preview, I'm going to talk about the central nervous system, the immune system, the blood-brain barrier, the immune system interacting with the central nervous system, and what happens during a bacterial infection in the brain. So, to start, slide. Can't get my slide to flip. Alright. So to start, the central nervous system consists of the brain and the spinal cord. And initially it was thought that the brain was immune privileged site. So what does immune privileged mean? Immune privileged essentially means that the brain is able to have a graft done, so like foreign brain tissue is able to be put on, and essentially there's no rejection. There's no fear of rejection. So essentially no immune response is occurring because it's accepted. So that's what immune privilege means. So that's essentially what they thought, because when they did grafts, this was occurring. But this wasn't right. I'll talk about that later. Now the immune system. The immune system consists of multiple organs and cells that interact within the body to help prevent infections and defend your body against pretty much infections if they do occur. Especially, disregard that last statement. Some primary cells that are part of the immune system are microglia and oligodendrocytes. Ooh, it's a tough one. Astrocytes, neutrophils, T cells, dendrites, as well as glial cells. And I'll talk about that. All of these cells later. Now, oh God. In the immune system, I need a tissue. Wow. In the immune system, there's sub-branches, two sub-branches. The adaptive immune response and the innate immune response. Now, initially when we get a foreign antigen or bacteria inside our system, an innate immune response occurs. And that's because an innate immune response is fast-acting, has no memory, and fast-acting, has no memory, and is not non-specific. It's just going to target anything that's just out there. So that's what's occurring right away. But that's not good in the brain. The brain, we want to find the exact cause of the infection and kill it, because we want to limit the damage done in the brain. So we need an adaptive immune response to occur. So something has to occur for it to switch over to an innate immune response to an adaptive immune response. So an adaptive immune response has memory. It's a little bit slower, but it's more efficient. It has lasting effects. It's specific as well as diverse, and it's able to determine self from non-self. Now, this sounds perfect in defending the brain, but we need to see how this switch occurs, and I'll talk about that in my later slides. Now, before I talk about my next subject, I'm going to talk still about the immune system, specifically neutrophil rolling. Now, neutrophil rolling is essentially the ability for neutrophils to enter the site of infection. So essentially your neutrophils are your white blood cells. They're in your central nervous system. Not your central nervous system, sorry. Your circulatory system, there we go. And during the source of infection, chemokines are released, and these are pretty much like signals to say, hey, come to this spot, we need you. So like during an infection, chemokines are released, and neutrophils pick up on those chemokines, and so they rush to the spot of infection, but they can't get to it, and so they're rolling past the site of infection, and it's not till they come in contact with integrin that they're able to start adhering to the surface and interacting with the surface. Now, when they're interacting with the surface, they're interacting with selectins, and these selectins are able to activate surface proteins on the neutrophil that in turn allow the neutrophil to transmigrate across the membrane and into the site of infection. It's really cool to watch. I wish I could show you guys a video, but for time's sake I can't. I could just say it goes like that, but it's sweet. So now the neutrophils are able to transmigrate through the membrane and interact within the source of infection, in this case, the brain. And I'll tell you what the neutrophils do once they're inside there later. Alright, so now the blood-brain barrier. Now this is where everything gets connected. The blood-brain barrier consists of a network of capillaries, and these capillaries are made up of endothelial cells with tight junctions, which is not commonly found anywhere else. As well as astrocyte feet, so those astrocytes are here, periocytes, and microglia. Microglia again. I'll talk about those later. It's on my eye. So, the blood-brain barrier allows passive diffusion of, where is that on mine? Of water, some gases, and lipid-soluble molecules. It also acts as a defense for the brain against bacterial infections. So it's essentially a shield for the brain, essentially. But previous research kind of proved that it was, and then shut that down right away. So what happened was, initial research had it so that what they did was they put dye inside the body, inside the circulatory system, and they observed what organs were being dyed after the circulatory system had done its process. And so what they found was most organs were dyed, but when they looked at the brain, they saw little to no staining. So they assumed that the blood-brain barrier is preventing interactions within the brain, like between the circulatory system and the brain. So essentially the immune system and the brain. Now, other research done was regarding grafts in the brain. And like I said earlier, one graft means immune privileged. Well, they tried 2 grafts then, and this is where immune privilege goes out the door. So what they did was they took 2 grafts, they put 2 grafts inside the brain, and what they found was the second graft didn't do so good and was rejected. Now, this indicates that the immune system is able to interact with the central nervous system, and therefore the blood-brain barrier isn't as impenetrable as we thought. So, now comes what? Now what? Now what do we think of the blood-brain barrier? Well, let's talk about what occurs during an infection. If I can get my slide to flip. So, in the case of neural inflammation, the blood-brain barrier begins to change. Chemokine production increases, and there's an upregulation of surface adhesion molecules. Essentially, T cells and other immune cells are able to enter the central nervous system. However, the amount that gets in is still kind of controlled, essentially, via the glial cells. The glial cells are the ones that promote apoptosis, and so essentially they kill your cells. And so when there's too much, the glial cells activate and they kill your cells. So just to make sure it doesn't induce an autoimmune response when there's too many immune cells within a certain area. Alright. So now that we have a little overview of the immune response during just an infection, let's talk about a bacterial infection of the brain. They're rare, but they're almost always life-threatening, and so therefore they're serious and we need to focus on them. Now, they often occur in three ways. One is direct destruction of the endothelial cells in the capillaries. Another one is disruption of the intercellular tight junctions and migration in between the endothelial cells. And then the final one is the bacteria is able to go into vesicles and transmigrate into the brain. Now, once a bacterial infection's inside the brain, the innate immune response kicks off right away and starts trying to defend the brain. But this innate immune response is not as efficient as the adaptive would be. So, now that the innate immune response is occurring, they need certain cells to kick off towards the adaptive immune response. And so the cells involved here are microglia, which initially phagocytose, and then after they phagocytose, they present the broken down bacteria as antigen for other white blood cells, or not white blood cells, but just immune cells to see and identify, so that they have memory and are able to target those specific things. Then the microglia also are able to break down the blood-brain barrier and allow more white immune cells to penetrate and into the central nervous system. Now, microglia's partner is astrocytes, and astrocytes essentially do everything microglia do. They just are partners in this. They also contribute to the gap junction stability of the blood-brain barrier in normal conditions. But during an infection, they release chemokines, and these chemokines recruit the neutrophils that I talked about in neutrophil rolling, as well as monocytes and T cells. And they upregulate cell surface adhesion molecules. So essentially, they're recruiting more and more immune cells towards the source of infection. Now, neutrophils. These are your primary defense. These guys are the big guys. They'll come in, phagocytose everything around them that they need to, that is specific, and besides killing a lot of bacteria, they also upregulate adhesion molecules again, allowing more neutrophils and other cells to come in towards the infection. And something that's interesting is that during an infection, the blood-brain barrier expresses selectins on it, and so it allows neutrophils to begin rolling, and so more neutrophils can come in towards the source of infection. It's essentially the blood-brain barrier wants the immune system to help, and this was not what we thought earlier. Besides that, neutrophils also release defensins, lytic enzymes and antimicrobial peptides, and these stay around in your body after the source of infection just to make sure that an infection doesn't reoccur in the same area. So it's kind of protecting the brain while it's down. So essentially, it doesn't get kicked while it's down. On top of that, it also releases chemokines that shift the immune system from an innate response towards an adaptive response. And when we talk about an adaptive response, we're talking about T cells. T cells produce interferon gamma, and this in turn leads towards the generation of chemokines, and they recruit monocytes and more T cells to the area of infection. And this drives the adaptive immune response even more. So, now that I've talked about what occurs during a bacterial infection, I'm just going to quickly review what I've talked about today. During an infection, the immune system signals for more cells to come into the source of infection. The blood-brain barrier becomes permeable, and it allows the immune system to interact within the central nervous system. The immune system also has checks and balances during this to make sure that an autoimmune response doesn't occur via the glial cells, which promote apoptosis of cells, essentially killing cells. Alright, and in conclusion, we've come to observe that the immune system is able to interact with the central nervous system because the blood-brain barrier becomes less permeable, becomes less immune privileged, and becomes more permeable to immune cells during an infection. Some future research would be to better understand the interaction between the immune system and the central nervous system. This in turn would lead to maybe possibly understanding how MS is occurring in the brain, which is a very serious infection, and essentially hopefully leading to a cure of MS as we begin to understand it. Alright, at this time I will open the floor to questions.